Welcome back. So we'll continue the final discussion on vertical axis wind turbine, which we started. So what we have done so far, we just recollect that in the vertical axis wind turbine, we also tried to look at different aspect of the vertical axis wind turbine. Then this uh, basic nomenclature of the vertical axis wind turbine, then the different types of, especially the lift based and the drag based, and then we try to analyze them as we have done in the horizontal axis wind turbine. And this is what, if you see in the last session where we stopped, finally we have found out um, these things, what you call the analytical expression for power coefficients and all these things. But there we have used two different theories. One is the single steam tube theory, the other one is the double steam tube theory. And obviously, these are simplified analysis to some extent. Obviously, with some kind of an, what you call, some kind of an assumption associated with that. Okay. Now, this is where we stop. So today, what we'll do, we'll finalize that thing. So now the another option that could be um, possibly this. So what we are going to talk is that the double multiple steam tube theory. So this is again extension. So this is an extension multiple steam tube theory. So what we have discussed about multiple steam tube theory. So this is the extension of that. Now, here the approach is pretty similar. One can think about the situation. So the approach is pretty similar to the multiple steam tube theory, which we have already described. Um, so here the only difference, so what one can think about, the approach is similar to this multiple steam tube theory. So if I short form like multiple MSTT, but the difference here is that there is a slight difference. Here, the induction factor in the upwind and downwind positions need not be the same. Okay. I mean, there are different, I mean, there's a double multiple steam theory based some simulation tool has been developed by Sandia National Lab. Obviously, one can devise that kind of tool and analyze that. So that much only we'll talk about here. We are not going to be very much detailing out about those details because that's not, I mean, essentially required at this moment. Quickly, we look at aerodynamics of Darius rotor. So, I mean, typically, if you see the Darius rotor, I mean, if you try to sketch it, so then you have one goes like that, then that come here is goes like that. Oh, and the other one is like that. So that would come. So that's the thing. And if we talk about that, the base plate, okay, and this is your main shaft, okay. So that is how, and then in between you have the other shaft and all this. Okay. Now, so the Darius rotor, this can be analyzed using single or multiple steam tube. So either of that one can use it, what we have already discussed so far. The main difference here to do with, so the main difference that one can, that is the, because orientation of the blade element, one, which are now different from one another, and the analysis that we have carried out, there is more like a single straight blade, and so one can say which are now different from one another. And the second point, which could be the distance of the blade elements from the axis of rotation, which is again, which is not constant with the length of the blades, length of the blades. So, I mean, these are the two major difference that one would encounter. If you see the previous single steam tube theory or multiple steam tube theory that we have discussed, uh, assuming some single blade or under certain simple, but realistically the Darius turbine would look like this. And so the analysis would be slightly different what we have done. So you have to probably incorporate some changes. And one of the reason is because of the orientation of the blade elements. You can see one goes convex, another goes concave, and the distance of the blade elements from the axis of rotation. So if this is the axis of rotation, then which is not constant. Okay. So I mean, more about this analysis, we will not go in the details within the scope of this particular course. I mean, one interested, they can go through the textbook which are available, which talks about only detailed analysis of various type of rotors. Okay. Similarly, we'll quickly talk about Savonius rotor. Okay. So this is also a kind of vertical axis wind turbine. Okay, kind of that, but this is S-shaped cross section when viewed from top. Okay, so top view shows like an S-shaped cross section. This was this is not Darius. This is not Darius. This is Savonius. Okay, so that's a small corrections here. So the picture is for Savonius. Please note the same. This is not Darius. Okay, this is the picture we are referring here. When you look at from the top, it looks like an S shape. So essentially, it is a drag type. So this is a drag type device. Okay, but there may be some amount of lift contributing to the power as well. Okay, so here the power in Savonius obviously is primarily based on the pressure difference across the blade, retreating from the wind, and that advancing into the wind. So the power calculation here is primarily based on the pressure difference across the blade, retreating from the wind, that advancing into the wind. This is essentially equivalent to the uh, difference. When I say that equivalency is the difference in the drag coefficients associated with the convex side of the blade and the concave side of the blades. Okay. So, I mean, there is a textbook by Parasitbu in 2002, which talks about detail of this Savonius and Darius rotors. So we'll not go into the much more details of this discussion. So again, please, this picture here that we have drawn, this is not Darius, this is for Savonius. So please make a note of that. So that was a correction. So we have, I mean, Savonius case, it is again, you have this convex and concave side of the thing. So the obviously drag type of device. Some amount of lift may contribute to the power production. So this is primarily the pressure difference across the blade, which is going towards the wind and coming out of the wind, which is again the difference between the drag coefficients associated with this convex and convex. So in general, what happens is that this Savonius rotors or turbine of low efficiencies. Okay. But although the power coefficient is close to zero point 0.3, so CPU would be close to zero point 0.3. And the peak power coefficient could reach a tip speed ratio of 1 or something like that. I mean, in general, it's a very low efficiency device. So obviously, there could be other issues which are associated with this Savonius kind of rotor or the turbine. Um, there could be issue with the, I mean, like each type Darius has some kind of a starting torque issues, whether Savonius doesn't have that, but Savonius power output is low, but whereas in the Darius type power is high. So one can think about some design which is a mixed in nature. So all these are kind of possibilities. So that's pretty much that we would like to talk about. So this vertical axis wind turbine and horizontal axis wind turbine. And rather, I would like to make an stop here and say that so we have done quite a bit of theoretical or analytical analysis how to design the blades of horizontal axis wind turbine and followed by this discussion on vertical axis wind turbines. Uh, but what we have not talked so far, I mean, this is what we have rather uh, discussed everything based on the aerodynamics of this horizontal or vertical axis wind turbine. So the aerodynamics, what we discussed, is primarily contributing to your power production. And then whatever analysis we have done or looked at it, how to improve your power output. Obviously, considering some of the efficiency of the different components and things like that, but that we have taken into consideration, and then how much power you could generate. So everything based on your aerodynamic analysis. Now, what remains not discussed so far is the part of the structural loads and all these things. So now, what we're going to look at the loads on this turbine. So rather, we look at some of them we look at as a component wise, and then we move to some looking at uh, the total the whole turbine unit and their loads and all these things. Okay. So as I've said that now we are going to look at the mechanics and dynamic of wind turbine. We start with some component level analysis, and then we could move on with that. Okay. So the first thing to do that kind of things, what we have to understand is what are the loads, okay, and forces. So that is important. Loads and forces are acted on the turbine. Where are the sources of these loads? Obviously, the primary load source is due to the aerodynamics, which contribute to lift and drag. You could have gravity, you could have inertia, which could be gyroscopic, and centrifugal. Okay, you could have electromechanical, that is generator rotor. You could have operational load, so which is coming from brakes, your mechanism, pitch actuator. Okay. So these are essentially your sources of loads. So what we have discussed in detail so far is this component, the component A, which is the aerodynamics load. So we have looked at everything, how you get lift, how the aerodynamics analysis could be done. But if you see the whole turbine unit is also having exposed to this gravity load, inertia load, you have electromechanical due to generator, operational loads and other things. Now we can also look at so these are the sources of loads, but we can think about what are the types of loads. Okay. So one could be, let's say, steady. That means it can be static and rotational. So it could be static and rotational. Okay. Then you can have cyclic. Okay. This can have in terms of multiples, which are essentially your harmonics, okay, of rotation frequency. So here we can say that 1p is that once per revolution, you could have 3p 3 times per revolution. Okay. So in generic, we can write BP, that means B times per revolution. And B here is number of blades. And one can say this B dot P as a blade passing frequency. Okay. So you could say that this could be my blade passing frequency. Fine. So the third load could be resonant, that is due to vibration of tower and blades. Then you could have transient load, which is due to your starting of the machine, stopping of the machine, yaw, all this. And there could be stochastic load. And this is primarily due to wind, because wind is turbulent and that could be kind of affecting that whole thing. That's what you have different kind of, I mean, a simple steady load calculation one can do. Let's say I have this turbine. This is my, and then I can have tower like that. So this way is weight, which is F of G. This is my thrust, so F of T, and the resultant could be like that. So this is a steady load during normal operation. Okay. So what you can, so these are the force components. So it's a schematic. So I mean, it's not needed to be very actual and things like that. Just to kind of demonstrate situation a bit details. So what you have, the FP is P by 2/3 U infinity, and Fg is m of the mass and G. So these are typical calculation of this. So you have the some thrust and all these things. So that's some, let's say, simple approximation of the thrust and all this. I'm not here trying to give you an exact thrust expression or things like that, because in order to include every effect, or it just to demonstrate how things can. So let's say, for example, you have power is 6 megawatt, your U infinity is 9 meter per second, and your aim is 360 ton. Okay. Then what this gives, if T would be, okay, it is by P by 2/3 U infinity. So essentially 6 megawatt by 2/3 into 9. So this would be 1 mega Newton. Okay. 1 mega Newton. And my Fg would be m into G, 360 into 10 to the power 3 kg, 9.81 meter per second square. So this would becomes 3.6 mega Newton. So that gives you an idea, kind of uh, quantum, or the forces that going to act on a turbine. I mean, it's a simple example, and we using a simple expression of the thrust, and obviously thrust includes uh, all the details. So this is what the whole unit in a total is exposed to. Obviously, the horizontal axis wind turbine exposure is much higher than the vertical axis wind turbine. One of the primary reason being the vertical axis wind turbine is very small in size. So that's the, so if I quickly recap the thing, you have different sources of loads. Primary loads comes from your aerodynamics, then you have gravity, you have inertia, which is because it's a rotating system, so gyroscopic motion, centrifugal motion. You have electromechanical system, which is generators and all these. You have some operational load because it suddenly breaks your pitch. And you could have different types of loading, static loads. You have, I mean, steady, which could be static and rotational. You could have cyclic loadings or revolutions, which is brings you the blood pressure frequency. You could have resonant, transient load, stochastic load. I mean, we'll go in detail analysis of all these, how you incorporate and all these things. And this simple example shows what kind of forces that would be acting on the body. Okay. So we'll stop here and continue this discussion in the next.